Welcome to another CO2 design fundamentals. We're going to dive into high pressure valves today. And what I really like about this, like we've done a ton of different design courses. We got a 12-week CO2 design course coming up, and we've done it multiple times. The biggest thing is that if you understand supermarket or commercial refrigeration design now, CO2 is not that much different, but there are differences. Diving in under understanding the high pressure valves and then these different valves that you're using in CO2. And today we're going to be diving into high pressure valves and how to select them, because we think this is really important to give you a good understanding of that system design. And this is why we do this. This is why we share this knowledge. This is why Chris is here. He's an expert at high pressure valves, designing CO2 systems. And we've been working with so many people around the world. And what we want to try to do is help you a little bit. If we can teach you one or two things that you can bring value to your customer, to someone in your organization, this is why we do this stuff. So Chris, how you doing, brother?
Thanks for having me, Trevor. It's nice to be back. Yeah,
Oh,
say, I
man.
missed
Oh,
this last week.
yeah, it's always good chatting with you, share knowledge because you care. You know what I mean? This is what we want to help more refrigeration professionals around the world. And these couple of tips will hopefully go a long way. And what we share with you here, share with other people. The how you get better is learning the same thing over and over. So it's 7 to 11 times. I said this many times on the podcast, on the YouTube. You got to do it a lot of times. You got to put those reps in, just like you're at the gym. Same thing in refrigeration. If you want to get good at design, you got to put the reps in. We're going to be diving into high pressure valves today. Super excited about this. So, Chris, let's just get going.
Let's jump in. So yeah, today, high pressure valves. So also known as a transcritical valve. I'm going to use the term high pressure valve. That's the term I've always been introduced to it with and have always used ever since. If you type in transcritical valve or high pressure valve, you'll get the same information online. So just to get terminology out of the way, they mean the same thing. A high pressure valve sits between the gas cooler and the receiver or the intermediate vessel. And effectively, it has two main purposes for existing, and that is to regulate the pressure within the gas cooler. So we can open that valve to release pressure from building up in the gas cooler and thereby reduce the outlet pressure, or we can throttle it and build pressure up within the gas cooler. The other purpose of this is as we create that pressure drop on our pH diagram, we then drop that transcritical CO2 refrigerant down in pressure to allow it to start condensing. So we partially expand it into our liquid receiver, and we're allowing us to get liquid again, what we can send off to our expansion valves. So what happens if we don't size this valve correctly? Well, as you can imagine, if it's too small, we're going to have excessive pressure building up in that gas cooler when we might not want it. Likewise, if it's too large, we'll be letting far too much gas out of our gas cooler, and we run through this in quite a lot of detail in the design course. But actually, we want to boost the pressure of our gas cooler to maximize our COP, our coefficient of performance, because as our ambient temperature changes, we need to boost our pressure to accommodate that and get as much sensible heat rejection as we possibly can. So sizing this high pressure valve is just as equally important as any of the other components we look at. So alongside that, we also get loss of efficiency if we size it incorrectly. If we oversize it, there's a lack of control. It's not as big an issue if you oversize as opposed to undersize, but you're spending more money for very little or no benefit. And then the last one there, noise and vibration. If we throttle it too much, same as any other valve, we're sending too much mass flow or trying to get too much mass flow through it. That energy is going to go somewhere. It's going to go into the body of the valve and shape the pipework around it. So how do we actually control these systems? Well, there's a couple of different manufacturers with varying control structures. On the right-hand side, we've got an example of a Danfoss setup, ICMTS valve. And effectively, from the gas cooler outlet, we'll have a pressure transducer and we'll have a temperature sensor. With these two bits of information, controller processes it, also talks to the compressors, the rack controller as well. Or it'll be incorporated into the rack controller generally. And from this, it will decide, well, this ambient condition and our gas cooler outlet temperature, well, I have this pressure inside the compressors, I want to continue running at this frequency, and I'll need to throttle the valve back to maximize the COP of our system by boosting that discharge pressure inside our gas cooler to reject as much heat as we possibly can. So what happens if we don't have this control strategy? Well, we get unstable compressor control, because they're going to constantly ramp up and ramp back as well, depending on the pressure. And also we're going to reduce the quality of the liquid being fed off to our evaporators. The refrigerant inside the receiver, the flash gas, is controlled effectively by the flash gas bypass valve, which we'll discuss in the next session. But all that liquid feeding in is dependent on the gas cooler's, well, the high pressure valve. That is what is creating that expansion effect to drop that pressure down and allow it to condense again. So they all need to work in tandem. So we need to have a really effective control strategy to achieve that. So on the right-hand side, we'll see with this controller, this EKC controller, you'll have the ICMTS and it'll also have the CCM valve there, our flash gas bypass valve, talking to each other, which will also then relay back to our compressor. So it's all interlinked. Many control manufacturers out there. We've got the likes of Danfoss and Corel. They've been doing this stuff day in, day out for 10 plus years now. They've got this stuff pretty well nailed. As long as you follow their strategies, you should be fine.
And as a designer, you need to understand how they work. You can size them and stuff, but I work with many engineers and designers where they are actually doing the support as well. So depending on what size your organization is, you design the system. You have to have a good idea on how this works for the design, so you can go back and do the proper calculations. Like Chris said earlier, how does it control? What does it control? Why is it controlling those different components like the gas cooler condensers? And when you understand that, you have a better understanding of the system as a whole as a designer, because you should be able to take those support calls and be able to answer that question for a technician and help them feel confident that what that valve is doing is actually doing what it's doing with the information they provide you.
As a designer, you may be classed as an applications engineer, where you're applying equipment which is manufactured to a scope of works. But as a desk-based engineer, generally, you'll have more time to go in depth and understand how this stuff works if you can take it upon yourself to go and do the research and ask the right questions than the technicians in the field generally get a chance to do. So take advantage of that and be their ally, be their best friend. I'm sure they'll find a way to return a favor at some point.
Totally agree.
So in more technical terms, the high pressure valve regulates the mass flow of refrigerant from the gas cooler into the intermediate vessel or flash tank, regulating the pressure in the gas cooler. And then on the right-hand side, this very helpful diagram from Corel's literature shows as we lift that discharge pressure, so our horizontal line at the top, say we were at 75 bar, 80 bar, 85 bar, you think, well, we want to boost the pressure, we're going to use more electricity, we're going to put more power into our compressor input. But by sending it along, as we drop through that high pressure valve, dropping our pressure down back into our receiver and condensing our refrigerant back into a liquid, we now have a much higher quality liquid than we would have otherwise. Our fraction of liquid to our flash gas has reduced from maybe 60% flash gas there, 50 there, 45 there. So we're effectively getting, in proportion, possibly 30% more liquid than we were getting otherwise to go off to our evaporators and actually carry out our cooling that we need to do on site. So that is why we may want to artificially raise the discharge pressure in an ambient where traditionally you might get away with 75 bar. Actual temperature, etc., is a bit lower. But we're not making the best use of our system there either. Furthermore, if we had heat recovery, we're now getting even more heat recovered along the top. So again, it makes sense to do. It's where we can take advantage of all these site-specific constraints and really maximize the value in this system by looking at certain control methods and not just relying on component selection. But we need to select components to work alongside this and achieve this. So with HPVs, high pressure valves, we tend to use a stepper type valve. It'll be a bipolar valve which will wind a stem in and a stem out for that fine capacity control over system, rather than a pulse width modulated system where you're closing, opening, closing. Don't really want to do that because it's not going to provide a stable refrigerant scenario in our gas cooler. Stepper valves are really good at coping with low loadings because you want this system to operate across a wide range of operations. We need to operate at a peak condition in the middle of summer and also low load condition in winter. Low load condition, well, hopefully we're getting it fully condensing inside the gas cooler and sending it in, but we'll still need to be able to throttle that valve accordingly. So we effectively oversize a valve, but we're going to have issues with oversizing in terms of cost and then control at higher conditions as well. The manufacturer software will generally say between 15 and 85% okay, and it'll try and give you a proper band, normally between say 50 and 80% where it wants to target the selection. So with that, we're going to run through a very quick selection that I've done in Corel software, looking at a high pressure valve. So once you've got access to our website, you've signed up. On the left-hand side, you've got electronic expansion valves. Inside there, you can input your project-specific information. So for example, application of a compressor rack, just chucked in information, refrigeration mentor, Amiga Solutions as an example, rather than sharing any customer data. And then we can start to select our system or what the valve needs to do. Is it an expansion valve? Gas bypass? Well, on the right-hand side here, we have CO2 high pressure valve. We could also select flash gas valve down here, which would be suitable for next time. As we click through, we can input the conditions our system is going to experience that we need to size for. So these are the peak conditions our system is expected to experience. So in the UK, we don't tend to get temperatures higher than 40 degrees Celsius. Depending where you are in the world, you may be well beyond that. Otherwise, that might be miles out of what you'd be planning for, but it has to be site-specific, region-specific. The mass flow rate is taken at full flow for your compressors at design condition. So at this point of the scenario, you would have selected your evaporators, you would have selected your pipework, your compressors, and then your gas cooler. So a full flow, mass flow of all our compressors is here. This is in kilograms per hour. You can also change it to kilograms per second, or I hadn't seen a way for imperial units, but I've just converted them on the right-hand side here. The gas cooler outlet pressure is taken from the effectively ideal gas cooler pressure, discharge pressure from your compressor selection, minus any pressure drop through your gas cooler. So this scenario here, I think we had 98.6 bar gauge discharge pressure and about 0.7 bar pressure loss through our gas cooler. And that is how we've resulted in this gas cooler outlet pressure here. Our gas cooler outlet temperature will be our design ambient condition plus the approach that we want to achieve. The lower that, or the tighter that approach, the larger our gas cooler will need to be, or the more powerful our fans or pumps will need to be to achieve this. A 2 degrees Celsius, or roughly 4 Fahrenheit approach should be fine. And then our receiver pressure. So we've gone for the lowest receiver pressure we expect to have. It's about 35 bar. We generally float our receiver between 35 and 41 in the UK. So about 500 PSI up to, I don't know off the top of my head, sorry, probably 600 PSI, 650 PSI. Sounds about right.
Yeah, depending on the design of that flash tank pressure, 45 bars, 652.
Yeah. Once you input that information, you can calculate, and it will give you this diagram here showing the conditions that we've input. So our high pressure valve, as it drops down, drops back into a subcritical state, and this is the position it'll end up inside effectively our pH chart. And then we'll have our pressure for our receiver here, which would equate to our 35 bar. And then it also give you the enthalpy points of the refrigerant at those conditions. Again, you can plot this all on a piece of software or even get a pH chart out by hand and plot it. unnecessary for this scenario, but it's just handy information to be aware of. So once we've input all that, it will give us a selection of valves, and we can filter that as well on the left-hand side. So we've got a working point between 15 and 95%. We can adjust that as need be. Generally, the software is not going to effectively allow you to select something outrageous, which isn't going to work. Yeah. Corel is very helpful for this. It will give you a green, amber, or red condition along the working point here. Select something in the green, that's okay. And personally, I always try and select higher up in the range because that says to me I'm going to have tighter control as I drop the requirement down as well. You can filter through various component selection criteria in terms of, is it copper? Is it stainless steel connections? I don't think you'd really want sight glass on it. I've never seen the benefit for it, but you could filter for that as well if they manufacture it. And then just other information, for example, maximum temperature or 70 degrees. 70-degree fluid temperatures at a gas cooled outlet would be very, very warm indeed. And I think it's probably beyond the scope of a standard refrigeration system. And then once you've done that, you can select the quantities you need. And then on capacity, as we view that, it will give us a lovely sliding diagram here. And it shows roughly 84%. We've got the mass flow rate that we require. So it's converted it from kilograms per hour to kilograms per second. So roughly 0.7 kilograms a second, or about 1.5 pounds. That should be pounds per second, sorry, not pounds per hour. And what we could do is plot that as we go down and see what the capacity would be at that working point. Well, that's all well and good for our summer condition, but do we want to make sure it's actually suitable for low load as well? Well, we need to know what our low load conditions are. So we'd go into our compressor selection software and our gas cooler selection and run the process again for effectively our minimum conditions. That's what we've done here. So in the winter, our mass flow rate has dropped from 2,500 kilograms an hour to 707. We've effectively quartered it. Our condensing temperature is roughly 15 degrees Celsius. We don't tend to go much lower than that. And I think some software won't even let you go lower than that either. It's not, compressor manufacturers aren't generally going to test that. I believe 15 degrees is pretty cold condensing temperature. Our receiver pressure will remain the same, and then we'll also have a little bit of subcooling as well here. So again, converted into units. And you'll see on the right-hand side, our diagram's changed. Instead of us just having the drop-in pressure through the high pressure valve from transcritical to subcritical, well, we've actually got condensation occurring now. Still goes through our high pressure valve to get down to our receiver pressure, but is a much, much smaller pressure difference now. We're looking at 51 bar down to 35. So that's 16 bar differential as opposed to 60. We've got a lot less motive force behind that valve. We need to make sure that valve is opening still enough to allow enough refrigerant through and not jeopardizing the quality of the liquid going through. But as you'll see, we've got a much lower flash gas percentage here, much higher quality liquid. Then from there, I made a note of the valve we selected previously, the E3V55CWR01. And you'll see now, if we selected that based purely on those conditions, it's pretty low down in its working point, its working range, but it is still acceptable. And that is the lowest condition we should expect to see on this system. If we can do this on the lowest end and you can do it at the highest end, great. We shouldn't have to worry too much more than that. And then just to check, we can see as well on here on our capacity diagram, our working point here, we've dropped from 0.7 kilograms a second and 1.5 pounds per second down to 0.2 or 0.4. Again, that should be pounds per second, not pounds per hour. And that's just an easy way to check that the system is working at design conditions of all ranges. And you could also go through and check your compressors at various stages and the valve at various stages. If it's at peak and minimum conditions, you should be okay. So just to summarize on that, when we select our valves, the valve capacity increases as that minimum condensing condition increases and reduces as the receiver pressure increases as well. So we're basically reducing that capacity, that motive force between the two conditions. But as we're in condensing, we have a lot more liquid going through anyway. That capacity is related to the mass flow rate of the system, same as all valves are. And that mass flow rate is basically related to the pressure differential across the valve. The more we have, the more it's going to pass through, as we saw in our summer condition versus our winter condition. If we increase that minimum condensing condition, we increase the pressure differential. Increasing receiver pressure reduces that pressure differential again, so we float that receiver condition up. So we want to select based on the lowest condensing condition to ensure that valve is sized to accommodate the lowest pressure differential across the valve as well. We need to make sure it operates at all those conditions, highest mass flow rate, lowest point. So that is a very, very swift run through of high pressure valve selection. There's a lot more in depth we can go into it and how it plays into a part in terms of what if you have a very low load condition, but a very, very, very high load condition as well. How do we balance that? We need to then have multiple valves. How do we balance multiple valves on the system as well? The control strategy for that. If you have affecting multiple gas cooler circuits as well, how do we achieve that? We could talk. I feel like this high pressure valve is one of those topics. When I was first introduced to it, it's like it drops the pressure there. Okay, great. And that's like, actually, you could probably spend a day looking at stuff on this, no problem, running through different scenarios, different selections, how the different manufacturers go through and control it as well. It's a great in-depth topic to get into, particularly if you've encountered them on site and had to rectify some issues if you found them.
Yeah. And then it dives in even deeper when you're using an ejector as the high pressure valve. So
yeah.
So there's so much on the design. And I think the big thing is if you're starting to size these or design these, use multiple manufacturer software. Go into Danfoss, go into Carell, go into Sporlan, go into Siemens, whoever the manufacturers the high pressure valve, and go check them out, or flash gas bypass valve, whatever it is, whoever you're using. I think Coppola makes some of them too. Who else? There's a lot of them out there that make the high pressure valves now. So go in and look in their softwares. This is how you get better. This is how you get better. And how you get even better is getting into a design course like the Advanced CO2 Design course, where we walk step by step and get you to design your own system and your own high pressure valves. And who do you use and why do you use them? Is the price, is that a factor? Can you get those high pressure valves? This is something when you're in design that you really need to understand. Like, if you can design the best system, but if you can't get the parts for that system at your local area, how long would that mean your system's down for? This is something important. Do you add two of them? Do you add a backup? What is the cost of the price? Are you doing a small store where it's like 5 cases, or are you doing a large one when there's 100? Is it an industrial? Do you have to put them in parallel? How do I size when I put them into parallel and I need 4 or 5 of these high pressure valves? There's a lot of things that you need to understand when you're designing a CO2 system, if it's big or if it's small. So I love it. I love it. Chris, thank you so much for sharing that.
Yeah, great stuff, Trevor. I'd say. Very cool, sir. I think, what was the last issue we had on a high pressure valve? I've not had one for a good long while. They're fairly robust. Did hear a story of someone having to manually operate a high pressure valve for several days or so, waiting to get a replacement. That sounds like a fun task.
Yeah. I think I did a podcast with my good friend Timo Kofo, when he used to work for Carell. So go check it out on the YouTube channel. That's not more on the design side. Well, it kind of is. It's on how to use it, where the contractor pulled off the head of the Carell valve and it's still adjusting and still think it's moving, but it's actually not moving. And then they put it back on and now your valve is in the wrong position. Same thing can happen with Danfoss. You pull that off, and all of a sudden it's adjusting, and then you put it back on. Then you're going to be lost. This as a designer, you need to understand this stuff. This is how you help, because when you can support your design, that's game changing. That is game changing. As a manufacturer, you designed it, you can support it. I love that stuff. Chris, any final thoughts?
No, again, it's an important component to work with. If you're fresh into CO2, it can be a bit daunting to find. You've now got not only 4 components, you've got 6 to worry about now, or 7 really, because of the flash tank valve, flash tank vessel. But it's the same principle as an expansion valve in a lot of cases. It keeps pressure up on one side and drops pressure through it on the other side. It may be changing, instead of sending liquid through to get a vapor, you're sending vapor through to get a liquid. It's not in reverse. It's just a different part of the system. So doing as much research as you can, getting to grips with some manufacturer's literature, all that stuff is going to help, particularly when you have to start designing it or working on this kit yourself. So education. There you go.
Yeah, and we got a course starting on the 25th. This is it. You're going to see more, depending, even where, it doesn't matter where you're at in the world. CO2 is continuing to grow. Do you want to be ahead of the curve, or you want to status quo? Check out this program. This is a program that has been game changer for so many people. Chris, thank you so much for sharing these few tips. And I look forward to seeing the next session on flash gas bypass valves and receiver pressure valves. Awesome.
Thanks, Trevor. Catch you all soon.
Bye-bye.